Okay, now we're getting serious.
We're getting serious. Okay, so let me just do this for a second. So this is the kind of view that you should have seen if the school had taken place on location. Unfortunately, we will have to settle for just the background. Now, let me see. Just need to, oops, sorry. Okay, so first, I would like to acknowledge a few people. I apologize for those of you who were already attending the morning session, but there'll be a repeat, and it will only be for this day. In any event, I would like to acknowledge several people who made this school possible. First and foremost, there is the program's director, Christophe Salomon. He's the one who entrusted us to put this program together, and then there are the two important people on location at the center. Unfortunately, you'll only see them the day when we take pictures of this meeting. Of course, virtual pictures, so there will be Annie Glomo, who's the administrator, and the assistant administrator, Muriel Gardet, and some of you have exchanged with her during the registration phase. The next batch of people I would like to acknowledge are those who helped put this program together and gave a lot of their time to make this happen. I will give their names just in alphabetical order. So there is Ralph Clayson from Würzburg. There is Masashi Kawasaki from Tokyo University, Jochen Manhart from MPI in Stuttgart. There is Andy Millis, who's Colombian Flatiron, Jean-Marc Triscone from the University of Geneva. I didn't put myself because you see me, so there is no point in doing this. Now, the kind of information that you may need is all there on the website of the school, so please refer to it. There are different tabs. The program tab lists all the relevant information about the schedule, about the format, and various information. You have also the possibility to visit the Mont Blanc virtually. So there is a link at the bottom of the of this poster, and you can do that. I would like to acknowledge also the sponsors who have generously contributed for this event. There is the Deutsch-Französische Hochschule, and Jochen and Ralph both are part of this, I would say, joint venture between the French university, my university, Paris-Saclay, and the German counterparts. There is also the University of Geneva, the Flatiron Institute. They've been very kind, and there is also CNRS, the French Research Institute, and they've also made this possible. Okay, so that's for the, I would say, the global presentation of the event. So we will be starting the 115th summer session of Les Houches. And then if I may, so we see here that the second speaker of the day is Antoine Georges. Now you see the name of the moderator underneath, so that's Daryl. And now what I'm going to do is I'm going to appoint Daryl as the co-host. Voila. So now Daryl has infinite power to direct this thing. And I will switch off my sharing.
Should I start sharing mine, Mark?
Yes, please.
Great. Thank you. Thank you, Mark. And it's my pleasure to introduce our summer school speaker for this afternoon, as well as tomorrow afternoon. Our speaker is Professor Antoine Georges. Professor Georges has 2 full-time positions on opposite sides of the Atlantic, and thus a very extended wave function. The first is at the Collège de France in Paris, France, where he holds the chair of condensed matter physics. And the second is at the Flatiron Institute of the Simmons Foundation in New York City, where he is the director of the Center for Computational Quantum Physics. Professor Georges received his bachelor's degree from the École Polytechnique and his PhD from École Normale Supérieure and the University of Paris Sud. He then proceeded to work his way up the academic ranks of those same institutions until a decade ago when he moved to the Collège de France, and about 3 years ago when he took on the additional full-time position as a director at the Flatiron Institute. Professor Georges' field of research is broadly defined: the physics of large and strongly interacting quantum systems. This includes materials with strong electron correlations, their modeling and theoretical description, but also the physics of ultra-cold atoms in optical lattices. In his research, he uses a combination of analytical and computational tools, many-body methods, and electronic structure techniques. He is best known for being one of the co-inventors of dynamical mean field theory, for which he was co-awarded the Europhysics Condensed Matter Prize of the European Physical Society in 2006. He has won many other prizes, and so as to leave some time for his lecture, I will just mention his most recent prize, which is the 2020 Ansur Rahman Prize of the American Physical Society for the development of the dynamical mean field theory as a tool for the computation of properties of strongly correlated materials. You can see that's quite related to the topic of his lecture today. Professor Georges has been elected to the French Legion of Honor, as well as Academia Europaea and the French Academy of Sciences. He has published hundreds of articles that have been cited tens of thousands of times. Please join me in welcoming Professor Antoine Georges to the 2020 edition of Les Houches Summer School, where he will now give the first part of his lecture entitled Understanding, Computing, and Controlling Transition Metal Oxides. For the participants, I would like to remind you that today's lecture, if you have a question, you should type it into the chat window. And then at the end of the 90-minute lecture, I will go through the chat to ask your questions to Professor Georges. So please, Professor Georges.
Well, thank you so much, Daryl, for this very generous introduction. Can you hear me okay? Yes, sound is fine? Okay, very good. So this is how I have been thinking about these lectures. The first thing I would like to do is to start this first lecture with a fairly broadband and general introduction to transition metal oxides, and in particular to the collective or emergent phenomena that exist in these materials and make them really interesting, with actually a special focus which will come as a conducting thread during all these lectures, namely how to control the functionalities of these materials. So That general introduction should last, I think, about half an hour, and will be fairly general and broadband. Then the second part of the lecture is going to be more in a real school mode, where I would like to teach a little bit about some basic notions that we need to know and have at hand to understand the physics of these materials, starting with their crystal structure and then gradually making our way towards their electronic structure based on these crystal structures. We'll see how far I get today into this aspect of the lectures. I will continue tomorrow from the point I stopped at today, gradually introducing the notions of strong correlations and how to handle them theoretically. So the lectures will start more like on the descriptive and phenomenological basis and gradually become more theoretical as we move on. Okay, so what are transition metal oxides? Well, you could think that transition metal oxides are something like this. This is a piece of rust, definitely a transition metal oxide of a very common form. I would say that in terms of material synthesis and preparation, our chairman today can do a little bit better nowadays than this. And in the lab of Darrell, we would typically have more something like this. And in fact, the ability to elaborate those materials in an extremely controlled way, basically with atomic scale precision or atomic layer by atomic layer, using a variety of techniques, but in particular, molecular beam epitaxy or MBE has really revolutionized this field in the last couple of decades or so. And I'm sure this is going to be a recurrent theme of this school. So, you know, whether it's rust or whether it's these more sophisticated and carefully elaborated materials, the first question you may want to ask is, what is a transition metal? What is a transition metal oxide? And I thought that this was useful probably for some of you to remind you where transition metals actually sit in the periodic table. So the transition metals actually correspond first and foremost to the gradual filling of the 3D shell of you know, the usual hydrogen atom atomic structure. If you start from here, hydrogen, this is actually the first time in the periodic table that the 3D shell is ever filled as you move your way up in heavier elements. And so this transition metal series of the 3D kind starts with scandium all the way to copper and zinc for the heavier ones. But of course, we shouldn't stop there. If you can fill the 3D shell at some point later on, you can also fill the 4D shell. And that defines another row here of 4D transition metal oxides, which has a number of interesting elements, such as niobium or molybdenum or ruthenium, which are also fairly commonly studied in oxide form in our field. And then still with heavier elements, you could consider filling the 5D shells, which lead to heavy elements, you know, from lanthanum to gold. These elements being heavier, they also have large spin orbit couplings, which make them really interesting in their own rights. So although I'm going to focus the most of the discussion on transition metal oxides, more broadly speaking, these materials fall into a broad category of what we call materials with strong electronic correlations, and I'll come back to what this means later on in the lectures. And those class of materials would contain many other ones beside transition metal oxide. They would also contain, for example, rare earth or rare earth compounds that correspond to the filling of the 4F shell with L equal 3, or the 5F shell, that would be the actinides. And they would also contain materials like organic conductors, which, because the molecules are far from one another, also display strong electronic correlations, or many of the very intensively studied dichalcogenides and their twisted versions. So the overall family is very broad. I will focus the discussion on transition metal oxides, but many of the concepts that will be introduced and phenomena that will be introduced in these lectures apply with proper changes to other materials. So one of the distinctive aspects of these materials with so-called strong electronic correlations is that they are a wonderful platform for observing and studying a number of emergent phenomena. So emergent phenomena meaning things that emerge at large length scales as collective behavior of the big assembly of electrons that are hosted by those materials. And even if you think of transition metals as simple elements, and you look at the periodic table, the transition metals are the first element that display magnetism, which is a collective ordering of spins. So this is a vivid proof that these are good hosts for collective phenomena. And of course, magnetism is also heavily present in transition metal oxides, as discussed later and discussed also this morning in Manuel Bibes' lecture. But there are a wealth of other phenomena that are hosted by those materials, including metal insulator transitions, superconductivity, and many others like ferroelectricity, multiferroicity, large thermoelectric powers, colossal magnetoresistance, all sorts of interesting phenomena. These phenomena are interesting in their own right. They raise fundamental questions in physics and chemistry, but they're also interesting because they present potentially useful functionalities, some of them being already a reality for electronic applications, and many others, probably many more others, being currently considered as possible useful functionalities. So to illustrate this, let me show you just in one slide, 3 different phase diagrams of such transition metal oxides, which are all rather old examples and time-honored ones. So here on the upper left, we see a material that was intensively studied in the 70s, but still of the past century, 50 years ago, but is still intensively studied in the lab. If you go to the APS March meeting, there's always a few sessions on vanadium oxides, even today. And V2O3, or vanadium sesquioxide, which is this material here, is really poised very close to a number of instabilities that cooperate or compete with one another. If you look at these materials, under low pressure, actually small negative pressure that you can reach by inserting chromium, although the correspondence between substitution and pressure is to be questioned and has been questioned here. You have a phase here, which is that of a non-magnetic insulator. I called it paramagnetic because it has fluctuating local moments. So you can think of the cartoon of the wave function of electrons in this material as just localized electrons on their crystal lattice sites with random spin orientations. If you look closely, the blue and red arrows are more or less randomly distributed. And as you increase pressure, if you are below 400 or so Kelvin, this material would undergo an insulator to metal transition through a sharp first order line where the resistivity actually drops by several orders of magnitude. And so what you reach here is a phase, which is a metallic phase, which is conducting. And this is sort of depicted here in a cartoonesque way by having also places where there are holes and double occupancies so that electrons can more easily move around. So this is a non-magnetic metal. And of course, if we go back to this side of the phase diagram, these random orientations of spin cannot really stay such down to low temperature. Something has to happen, if only to suck out entropy of the system. And what happens, as may be expected, is that these spins order antiferromagnetically. So you see that here you have a phase which is an antiferromagnetic insulator. And if you tweak this system a little bit, there is an additional fourth phase, which is an antiferromagnetic metal. So you see the beauty of such a material in which, by varying such control parameters as temperature or pressure or strain in a broader context, you can actually switch the system between a number of different phases with very different physical properties, both from the point of view of transport and from the point of view of magnetism. Here on the upper right, there is another very widely studied example, which is the famous manganite materials, where depending on the relative concentration of lanthanum and strontium and also on temperature, you can have a wealth of different phases. I just can't count them right now, but there are at least 7 or 8. And these phases differ by their magnetic ordering, but also some may be antiferromagnetic, some others ferromagnetic. And they also differ between one another from the fact that some of them have a certain degree of charge ordering, which make these materials very interesting. And then, of course, turning to the bottom right corner, this is the infamous family of cuprate superconductors, which provoked a kind of revolution in the field of superconductivity back in 1986, when their superconductivity was discovered, leading, of course, to the Nobel Prize of Bendorf and Müller. And you see again that by varying temperature and especially doping, by substituting strontium in the place of lanthanum, for example, you can have a host of a variety of different phases, such as a magnetic insulating phase near zero doping or superconducting state when the system is doped. So I'm not going to, describe these materials in further details right now, but I just put together these phase diagrams to illustrate the fact that these materials have many possible phases that compete with one another. And this is not only the case of these 3 families of materials, but this is very generic to all these systems. And presumably this means that since we can switch from one phase to the other with relatively small changes of physical or chemical parameters, this means that the energy differences between these different phases, or the free energy differences, are rather small. So this is actually a blessing, because it means that you can have a lot of action by changing some control parameters. But it's also a challenge, because if you want to control the materials and not get some random phase, but actually know what the material will be doing and possibly be able to switch them in a controlled way from one phase to the other, you need to devise control mechanisms. And many of these control parameters have been known for decades in the bulk, and it all starts with chemistry, obviously. You can change the chemical, I can't, but chemists can, or Darrell can, change the chemical composition of the material, and you can do that with or without injecting extra charge, with or without doping. You can also use the physicist tool like pressure or strain control. And the more you do that in a controlled way, the more you can actually control the functionalities of these materials. Here in this little table, I've tried to assemble the following information. In the left column, you see some key physical parameters, which will come back later in the lecture, that are important to decide in which phase the material falls and what it does. So, important electronic aspects. Jumping ahead in the lecture is, of course, the bandwidth of the relevant bands near the Fermi level. But also importantly, and this will be something I'll talk more about in this lecture, is the degree of orbital degeneracy or crystal field splitting between different orbitals. But of course, also the filling of the shell and associated doping, and dreaming a little bit the possibility of controlling the interaction strength, perhaps through control of screening. And in the second column, I've tried to put in some of the established, or if you want, time-honored ways of controlling these different parameters using the tools of the chemist or the physicist, mostly in the bulk. So, you know, to control crystal field, to control bandwidth, you can use pressure, you can use the size of the rare earth, which, as we will see later in this lecture, will control the distortion of the crystal structure and hence change the bandwidth. You can control crystal field also with the size of rare earth or change of what's called the tolerance factor that I introduce later. You can use doping substitutions to change the filling of the shell, and so on. And then on the column in the right, which is written in red, I've tried to emphasize some of the more modern or more recent avenues for achieving similar goals. And I'd like to basically emphasize two of them. One is a very important theme for this school, and I already mentioned it. It's the ability to actually elaborate those materials in a very controlled way, and not only elaborate them in a controlled way, but actually combine different materials, either to control one with the other, or to generate a new functionality of the sandwich, which actually Darrell has a beautiful picture with a sandwich. He has to show that at some point, which you know, would display a new functionality that neither the ham or the bread individually have. So that's one modern route towards control. It can be MBE, but it can be other elaboration methods such as pulse laser deposition or other methods. And there is another route towards control, which is very intensively studied by a number of groups, which is the possibility of controlling these materials with selective light pulses. Of course, here we are talking about mostly about transient control, which would take us into the research direction of non-equilibrium physics. And I'm not going to talk about this at all or very much in those lectures, but you should just note that this is an interesting current direction in the field. Okay, so let me elaborate a little bit more on the first aspect, namely the elaboration of controlled, atomically basically controlled artificial materials. So this is a picture of one of the pioneering early works. There are several other that appeared at similar times. This is a famous paper by Harold Wong's group when he was still at Bell Labs, where he was able to synthesize by MBE a sandwich between lanthanum TiO3 and strontium TiO3. Strontium TiO3 is a famous band insulator, very high kappa dielectrics, which is an almost ferroelectric actually. And lanthanum TiO3 is what's called a Mott insulator. I'll come back to what that means later in the lecture. And what you see here is a sandwich made of single layers of lanthanum TiO3 in white, separated by a number of layers of STO. And this material I'll come back on later as an example of something in which the property of the sandwich is different from the property of each of the components for rather simple reasons in that case. Another material that I will use often in those lectures, and I'm sure will come back in the other lectures of in this school, because many of the lecturers have actually worked recently or in the past decade on this family of materials, are the rare earth nickelates. So R here is one of the rare earth of the 4F series of elements. And this material is a good example of two things. First of all, the interplay that exists between structural and electronic degrees of freedom. So again, here what you see is a sort of phase diagram where the vertical axis is temperature and the horizontal axis, well, it's not really an axis, it's actually more the different rare earth moving from the larger one, lanthanum, towards the heavier, but also the smaller one, lutetium, through praseodymium, neodymium, and so on. And for those who don't know that, the rare earth have these remarkable properties that as you make them heavier, the ionic radius goes down in size. This is because the attractive potential becomes higher. And that's called rare earth contraction. And as you contract that rare earth, you see that these materials, starting with praseodymium nickel oxide all the way down here, have a transition as a function of temperature between a high temperature bad metal to an insulating phase, which is displayed in blue here. And you see that just by changing the size of the rare earth, so for the larger one, praseodymium, to the much smaller one, lutetium, you can change that transition temperature of the metal insulator transition from basically 0 in the case of lanthanum all the way to about 600 Kelvin in the case of lutetium. So this is a very beautiful example, potentially useful, in which an MIT can be controlled by structural properties in a very, with a large amplitude. This family of materials have many intriguing aspects. As you see, again, it's an example with a free phase diagram. There is a metallic phase here. There is a non-magnetic insulating phase here, which has a special kind of distortion where every other octahedra is smaller, every other octahedra is larger. So there is kind of a breathing mode in the insulating phase that develops. And this insulating phase here is not magnetic, while at lower temperature, this insulator orders into a magnetic phase with a specific form of antiferromagnetism. So leaving aside lanthanum nickel 03, which is always metallic, you see that the metal insulator transition in this material can go either from a metal to a magnetically ordered insulator for praseodymium and neodymium, or from a metal to a non-magnetic insulator, and then later on at the lower temperature to a magnetic insulator for all the other rare earth elements. So again, a lot of action in a single set of material, in a single family of material, and evidence for a very strong coupling between structural aspects and electronic aspects. And in fact, rare earth nickel oxides are a good example of the ability of controlling these materials with many of the more modern tools that are that I mentioned before, basically all of them. So here what you see is data for resistivity versus temperature of neodymium nickel 03, so one member of this family that has an insulating to metallic to magnetic insulator transition. And you see how you can actually switch or move around the transition temperature and also change the amplitude of its hysteresis by changing the substrate. So this is Nd nickel 03 grown in rather thick form on a number of different substrates. Some of these substrates, like this one, correspond to what's called compressive strain, namely a smaller lattice spacing than the bulk lattice spacing. Those correspond to so-called tensile strain, namely elongating the lattice spacing. And you see that for those ones, you can completely suppress the metal insulator transition, while for those ones, you can actually move it around more or less at will. So this is a beautiful example of strain control using the ability to fabricate thin films on controlled substrates. But you can also control this phenomena by injecting charge carriers. And this is done here, not by substitutions on the rarer sites, but actually by using ionic liquids to inject charge carriers in the system. And again, you can move around this phase transition using this ionic liquid gating. which is something which is very useful to be able to dope by getting an electrostatic effects, these materials in thin film forms. And the ultra-fast light control has also been documented in this paper and several others for this family of nickelates. So this is really an example where on a single family of material, you can use all these tools in the modern toolbox that we have, or that experimentalists and chemists have, to be able to actually control the properties of these materials. Okay, so this is all about control, but there is, of course, the ultimate goal is also design. And I've already talked about examples where you can use thin films and heterostructures to your benefit to control a functionality which already exists in the bulk. That was illustrated by the nickelates. But even more interesting is the possibility of engineering a new functionality by combining two or more materials, such as to reach a functionality which was not present in the bulk form. And there is also a third route, which is really interesting, which is more or less gives the name to its to this school, which is the ability of generating interesting electron gases at the interface between such materials. So let me briefly illustrate these to conclude this, these two last points to conclude this introduction. This is an example, again, I already showed it, of LTO and STO sandwiches. And STO is a band insulator, LTO is a multi-insulator, as I mentioned before. But when you make this sandwich actually has metallic properties. And the reason why this happens in this case is fairly easy to understand. It's because you can have a charge transfer from the titanium 3+ band of lanthanum TiO3 into the MTD shell of STO, in which the titanium in the bulk is nominally 4+. So you can have part of an electron which jumps from some of the titanium 3+, which get converted then into 4+, into the STO. And that basically amounts to doping LTO and hence to metallic properties. And in fact, this can be documented. These are results obtained using electron energy loss spectroscopy from that paper, in which the fraction of titanium 3+ here in the bottom right is monitored as a function of the number of layers of the LTO sandwich. And you see that when there is a single layer of LTO, like in the previous picture, there is only about a third of the titaniums, which are titanium 3+. So the system is significantly doped. It's a mixture of titanium 3+ and 4+, and hence it's expected indeed to be metallic. While if we increase the number of layers at about 5 layers of LTO, we get almost 100% titanium 3+, and we are back to the bulk behavior, which is a multi-insulator with a moderate gap. So this is a simple example, but a beautiful design example of how you can actually engineer metallicity by charge transfer between two insulators in the bulk. And there are some much more sophisticated and complex examples of similar phenomena with different functionalities. This is an example from the group of our chairman, in which a new room temperature multiferroic was actually engineered by making a sandwich between two materials, which are mentioned here, 113 and 214 perovskite, which leads to properties that were not present, as far as I understand, in the bulk form of either one. So this is a typical example where the sandwich has more interesting properties than the components, and you can get a bonus by being able to combine these materials in a controlled form. Now, to illustrate the third point of the slide I had before, very briefly, because I'm not going to talk about it really in my lectures, but I'm sure many other lectures will deal with that. you know, one of the big things in this field has been the ability to create 2D electron gases and electron liquids at oxide interfaces with interesting properties. So you could ask, well, you know, what the hell, we can create 2D electron gases in MOSFETs, or we've known how to do that for decades already. Why do it at oxide interfaces? Well, doing it at oxide interfaces leads to more to electron liquids than to electron gases, namely to electron gases with interesting interaction properties, and hence new phenomena typical of strong correlations that you wouldn't find in gallium arsenide electron gases. So this is one more example of what Herb Krömer in his Nobel lectures illustrates by saying often it may be said that the interface is the device. Indeed, in that case, the interface is the device. And of course, the big fish in this field has been the discovery of superconductivity at the LAO-STO interface. That's the original paper, and you see that several of the organizers of the school are co-authors of this paper, including Marc Jean-Marc and Jochen Mannert. And I'm sure we're going to have lectures on this topic later in this Les Houches school. This led to a nice prize as well. Okay. So if you want to see Jean-Marc with a tie, oh no, he doesn't have a tie. Terrible. Okay, so this is a slide that I put back for Darrell because I know he sort of likes and hates it. As you see from all these previous examples, what is really at stake here is the ability to design and make something new out of existing materials, or materials we can synthesize. And the new emergent collective properties come from the fact that there are interactions and correlations between the different degrees of freedom in the system. So the lattice, spin, the charge, and the orbital degrees of freedom, as illustrated by all the previous examples. And if you open a recent review article, many recent review articles in this field, you'll typically find, you know, this sort of cartoon that depict the entanglement of these different, and the interplay of these different degrees of freedom. This is conspicuously similar to the sort of thing that you would find if you open, I don't know if you do that often, I don't, all the alchemy manuals or textbooks from previous centuries. I find there is a remarkable graphic similarity between these two cartoons. Hopefully this is real science, and I leave you to judge whether this is, but definitely in a certain sense, what we are trying to do here is not to turn dust into gold, obviously, but it is to turn, you know, an insulator into a metal, or a material which is not multiferroic into a material which is. So we are also transmutating matter, this time using science and controlled principles, as well as clever design. Okay, so what are the keys to sort of success in this field? In my opinion, it relies on this magic triangle, which really should be drawn. I mean, a triangle drawn in this way looks highly unstable, but I don't know how to draw it in a different way. What I want to illustrate here is that the base, the ground that makes all the field possible is really material science and chemistry. So it's the ability of chemists to invent new materials, of people who elaborate materials, to elaborate them in an atomically controlled way, using all sorts of sophisticated tricks. So it's the design of new materials and the new elaboration methods that are really the ground on which all this field relies. And that is what allows then experiments to come in. And I would actually argue, if you were a funding agency, but hopefully you're students and not a funding agency, that this field has allowed to push and to, you know, to push the limits of basically all instrumentations and experimental techniques in our field of solid state physics. When you think of ARPES or STM or STEM or many other spectroscopy or experimental techniques, instrumentation, all of these methods either were barely existing 30 years ago or have been pushed to new degrees of sensitivity thanks to the study of these strongly correlated electron materials. So not only are these tools essential to understand these materials, but these materials are also a fantastic opportunity to push further the tools. And then here, somewhere in the right corner, there is theory. Theory is also moderately useful in this field. The phenomena that are at hand are very complex because they involve many degrees of freedom, many particles and strong interactions. So they are about the most horrible problem you can think of. But these things are also what make the collective phenomena emerge at large scales. So the field of theory, which is basically using a combination of analytical and especially computational tools, has made tremendous progress in the past couple of decades. What we were able to understand and calculate about such materials like transition metal oxides and many others 20 years ago is very little as compared to what we are able to do today. And that's not always very much appreciated, but I think that there's been tremendous progress on the theoretical and computational side as well. And hopefully some of the things later in the lecture will illustrate that. Okay, so that basically ends my broadband introduction to the field, and at least a small portion of the field that I could review in this 30 plus minutes. And now I would like to tell you a little bit what I intend to do in the remaining little less than an hour. So as I promised, I'm going to go a little bit more into lecture mode and introduce some basic notions about the structure and electronic structure of transition metal oxides. I will start obviously with crystal structures, focusing mostly on perovskites for two reasons. One is that it's a very rich and interesting structure, which is very often found among oxides. And two is that this is one of the only crystal structure that a simple theorist like me can understand. So why not talk about it? So that's, that should take about 15 minutes or so. Then I'll move a little bit more towards electronic structure by talking about crystal field theory and crystal field splitting, which is really important in this, all this business. I'll come back a little bit then on crystal structure aspect by talking a bit more about typical distortions of these perovskites and how we label them and why they actually are crucial to act on crystal field effects, precisely, that I have introduced before. And then, time permitting, I will make my way from this structural consideration towards electronic structure consideration, explaining how you go from crystal field theory to band structure with modern tools such as density functional theory. And if I don't have time to reach point 4 today, well, that will be left on the menu for tomorrow. Okay, so let's start with crystal structures. So before we go to perovskites, let me start with something simpler, namely monoxides. So we are actually considering here a transition metal, which here I've taken the 3D row, and you see here that this corresponds to the gradual filling of the D shell, right? In combination with oxygen. And so the simplest material you can think of is just take one of these elements together with the oxygen and make a monoxide. And so many of the monoxides actually crystallized in the simplest crystal structure on Earth, namely the sodium chloride structure, illustrated here on the right. And this is an occasion to think about nominal valences. As you know, oxygen is very electronegative. It likes to fill its 2p4 shell by capturing 2 electrons and becoming oxygen 2-. So the nominal valence, at least of a monoxide, is going to be that the metal is in the 2+ configuration and the oxygen is in the is in the 2- consideration. Here, a word of caution is actually necessary, because in the solid state, oxygen should not always be thought of as 2-, especially when you go to the right of the transition metal row of elements. The oxygen states become quite close to the metal states. And this can lead to situations in which the oxygen is not really 2-. And in the jargon of chemists, this is called ligand holes. It means that there is a hole in the 2p6 shell, or a partial hole of the 2p6 shell of the oxygen. So oxygen is not really, could be not really 2-, but 2- epsilon minus. And this is important for a number of transition metal oxides, especially the heavier ones. But at this point, let's just imagine that we have the metal in the 2+ nominal state and oxygen is 2-. This is a good approximation for something like manganese oxide, for example. And these materials are, well, a little bit boring, not quite boring, but they don't do so much. And especially because there are two elements, they can't be controlled so accurately. So typically what these materials do is that they are insulators of the mod type. I will come back to later in the lectures to what this means. And here you see on the example of manganese oxide, cobalt oxide, and nickel oxide, that they are all antiferromagnetic Mott insulators with Néel temperatures that vary between 100 or so Kelvin and 500+ Kelvin, a very high one for nickel oxide, with insulating gaps that have are several electron volts. So this being a two-element structure, you could control that by strain and so on, but there is not too much chemical controllability. And this is why I'm going to quickly move towards the structure of ternary oxides, which offers a lot more richness and room for control. So, of course, there are oxides involving three elements that do not crystallize in perovskite form, but many of them do. This is a very beautiful crystal structure, so the perovskite crystal structure, which I'd like to spend a couple of minutes describing in more details, because it will come back on and on in these lectures, but I'm sure in many of the other lectures of the school. So this crystal structure is made of octahedra of oxygens. These are blue atoms, which surround the transition metal ion, which is here in red. So you may want to call it ABO3, like it's often done. B is the central site, A is the guy in between, and O is oxygen. It would be a little more logical to call it RMO3, where M is the metal and R might be a rare earth, but it's your call. So the important thing here is that the transition metal is really encapsulated in a little cage of oxygens, and that's really important to keep in mind. And in this example, in the pristine cubic perovskite structure, the octahedra are nicely joined by corners, like in this drawing. And in the voids in between this network of octahedra, there is this third element here in yellow, which could be, for example, a rare earth. So this is the structure of many of the things I've already talked about before, or of this material here, which is a moderately correlated metal. And why are perovskites called perovskites? Incidentally, that's a little historical remark. Well, they are called perovskites because they were discovered by a guy called Rose, who was a German mineralogist and who was sponsored by Count Lev Alexeyevich Perovsky, who happened to be the Minister of Interior of Tsar Nicholas I, but also an amateur mineralogist. And the same way that we acknowledge various funding agencies for support, Rose, in a somewhat more elegant way, I have to say, Rose baptized his discovery of this material, calcium TiO3, which was called perovskite, which he called perovskite in the honor of Count Perovsky. So he discovered this material somewhere, I think, in the Ural Mountains, if I remember correctly. This guy actually has a material named after him as well, called roselite, which I'm not sure what it is. And but so he discovered this material, but he didn't figure out the atomic structure of this material. Of course, the crystal structure. I mean, X-ray were not invented at the time, and certainly not X-ray crystallography. And this was done later on. And I want to emphasize two names here. One is Victor Goldschmidt, who is a pioneer of geochemistry. He first described the perovskite structure. He introduced the notion of tolerance factor and also coined the term lanthanide contraction or rare earth contraction that I mentioned before. And this woman here, Ellen Dick Mego, who is a pioneering Irish-born crystallographer, who was the first to establish the perovskite structure using X-rays. I'm actually very envious of these two people because they both have a mountain range or an island named after them in either Spitsberg for Goldschmidt or Antarctica for Mrs. Mego. And they also both, certainly Mego has a material name after them. So that's a fantastic achievement to have a mountain ridge named after you when you study geochemistry. Anyway, so that was the one recreational slide, let's say. Let's go back to more serious science. So the perovskite that I presented is the structure of AbO3 or RmO3, but it can be seen as the limit of a very large family of material, which goes under the difficult to pronounce name of Ruddlesden Popper series. And that comes with this chemical formula, Rn+1 MnO3n+1. One of the most famous set of materials in this family is lanthanum-2 copper 04, which is one of the early discovered cuprate parent compound superconductor. And this is like sort of elongating the perovskite structure and putting additional rare earth layers in the middle, sort of separating the octahedra. And so here you see the first of this series, which has n=1 in this nomenclature, which forms these layers here you see of the MO2 form, so copper O2 in the case of lanthanum-2 copper 04, separated by these rare earth layers. And then another layer here. So this is the family of so-called single layer materials. And this can be repeated. Here you have an example where you have two subsequent layers and then a void and another set of two subsequent layers and so on and so forth, tri-layers, quadri-layers, and so on. And in that nomenclature, the sort of infinite, the cubic perovskite I presented before would amount to take formally the limit n goes to infinity. So the system becomes just three-dimensional. And you would get RmO3, which is the case I mentioned before. So it's a whole family of material. And I'm showing this not just for curiosity, because this introduces an additional control parameter, which is dimensionality. You see that in the case of the single layers, you have these very two-dimensional planes, which are widely separated. And so these materials are going to be very anisotropic with good conduction when they are metallic in the AB plane and poor conduction along the C axis. So dimensionality is another control parameter, which is important to have in mind for those materials. Okay, one of the things about the perovskites is that they are by far not all cubic. Actually, the cubic ones are to a very large degree the exception. And they undergo distortions to be just so that the atoms fill the space as best as they can, and due to electrostatics. And here I've grossly exaggerated some of these distortions. So the distortions are made of tilts. So the vocabulary here can be rather confusing. So usually it's customary to distinguish between tilts, which are rotations along, say, the A and B axis, which tilts or buckles the MO2 planes, and rotations, which would be rotations along the Z axis or the C axis of the crystal, which sort of, change the metal-oxygen-metal bonds in plane. So there are tilts and rotations that are very important. And actually, for reasons that I'll explain in the next slide, these tilts and rotations are especially large when the size of the rare earth becomes small. So when you have a very big element here in the yellow place, it tends to stabilize the crystal structure in cubic form or tetragonal form. And this is the case, for example, often of barium. If barium sits here, which is very large, often like in barium ruthenium 03, you have a cubic structure. But if you move to a smaller yellow atom like strontium ruthenium 03, you would have tilts and rotations. And this leads to the notion of tolerance factor, which was introduced apparently by this guy Goldschmidt and is very often used in this field. The tolerance factor is actually measuring how far we are from ideal packing by hard spheres. So if we imagine that given the valence of R and M and oxygen, so like for example, if we have strontium VO3, strontium will be nominally 2+, and vanadium will be nominally 4+, and oxygen 2-. Each of these ions have a nominal ionic radius. Of course, all this is to be taken with a grain of salt, but you can find these numbers in various books or tables. And if you think of these ions with their nominal charge as having a certain atomic radius or ionic radius, you can devise very easily by simple geometry, which is illustrated here, a condition for close packing where these spheres actually fill space. And you will discover that the ratio of the rare earth and oxygen ions, ionic radius divided by the metal plus oxygen ionic radius times square root of 2 is equal to 1 when there is ideal packing. So this leads to the notion that if this ratio is indeed 1, and this ratio is called the tolerance factor, you're likely to get a cubic perovskite. And if this ratio is smaller than 1, then typically the system will deform by rotations and tilts, lowering crystal symmetry, typically to orthorombic or monoclinic or rhomboedral, depending on the case. And it's an empirical fact that if you try to make T too small, then the system just is simply unstable. And as far as I understand, often cannot be synthesized. None of these numbers here should be taken, as you know, written in stone, but this is just a ballpark estimate of what's known in the field. So coming back, to the phase diagram of nickelates, each of the material was labeled before with the tolerance factor, and tolerance factor close to 1 gave metallic behavior, lanthanum nickel 03, while the tolerance factor significantly smaller than 1 indicates large distortions, which also came in the phase diagram with a very high value of the metal insulator transition. Okay, so all these aspects offer control on this material, on the material. And the beauty of the perovskite structure is that there are 3 sites on which you can do something, and especially there is this third site as compared to monoxides, which is the rare earth site, or the R site in my RMO3 notation, so the A site if you want, where you can do something to control, for example, not only the distortions that we just saw, but also the nominal valence of the metallic ion. So for example, if you take lanthanum TiO3, lanthanum is 3+, and this leads to titanium being nominally 3+, and 1 electron in the D shell. If you do strontium TiO3, strontium is 2+. This leads to titanium 4+ for neutrality, and hence the D0 configuration. So just by counting, you can be sure that strontium TiO3 is basically a bond insulator. And lanthanum TiO3 is open for discussion. It could be a metal, or it could be an insulator, but an insulator of an interesting type because it has a partially filled D shell. So from band structure, it's nominally not going to be an insulator. It turns out it is an insulator due to interaction between electrons, in that case with a relatively small gap. So the R site offers opportunities for controlling both structure and electronic valence. Okay, Again, that was the phase diagram of nickelates, where the tolerance factor was controlling everything. I just mentioned the infamous word of Mott insulator. So the Mott phenomenon, on which I'll come back later in these lectures, obviously, is this possibility or this observation that several of these materials that have partially filled D shells, and in the absence of magnetic ordering, let's say, would typically be metals from band theory point of view, actually turn out to be insulators. And that is due to interaction between electrons, or what we call strong correlations. And this is a rather complicated but very useful map of our friend Atsushi Fujimori in this early paper, and also in his famous RevMod Phys review article, where this is a little map where you can get oriented in the worlds of RMO3 or ABO3, 113 perovskites. And you should read this in the following way. Here, each tick here signals a nominal occupancy of the D shell. So for example, all these materials here have nominal occupancy D1. It could be here because we are considering a vanadium, a vanadate, which has vanadium 4+, which is D1. Or it could be because we are considering a titanates, which in this case, because there is lanthanum, is titanium 3+, and also titanium 3+, D1 again. And the vertical axis here indicates materials that have a larger ratio of on-site interaction to bandwidth, while those one below have a smaller ratio of on-site interaction to bandwidth. And so what you see here is that there is a boundary that separates materials that are metallic, these are the ones in the white region, and the ones that are insulator, which are materials in this gray region. So here you read from this chart that strontium VO3 and calcium VO3 are D1 nominal materials, which are metallic, while lanthanum TiO3 and yttrium TiO3 are also D1, but which are insulating, and in which here the metal is in the 3+ state. This one is placed below this one because it has a smaller gap. This one has a gap about 1 eV. This one has a gap which is only like 0.2 eV or something. And so you can see in this map that many materials which have partially filled D shell, as indicated here, fall in this gray region, and indeed are insulators for reasons that to a large extent have to do with this Mott phenomenon, but also with additional complications like charge ordering or other things. And if you look carefully here, you will see also that there is a certain trend of this boundary. And you see in particular that the D3 configuration here is particularly, it's particularly easy to get insulating materials. It's actually difficult to get perovskites with D3 configuration that are metals. And there is a reason for this that we'll understand later in the lecture, which is that D3 corresponds to the half filling of a partially filled subshell of the system that is called the T2G subshell of the full 5 orbital D shell. And being half filled, it's actually even more sensitive to interactions and hence to becoming a Mott insulator. So you see that with simple description and understanding of the basic structure and electronic structure of these materials, one can already go a long way. There is another nice map that you can also find in this review article, which this time emphasizes the ability to dope the system. And again here, what you see is that you can go, for example, from strontium VO3 to lanthanum VO3. I think the black bar here just indicates what can be done from a bulk synthesis point of view. Okay, so these are for the 113 and these for the 214. So this is just to illustrate that there is a variety of behavior as far as the metal insulator transition is concerned, and that this phenomena is actually very important and dominates the physics of this system in many ways. I already mentioned this, the ability of creating a metal out of two insulators. I'm not going to go back on this. Okay, so that more or less closes the basic notions I wanted to introduce as far as structure is concerned. As you see, as I promised, I only described the perovskite structure and the various perovskites of the Ruddlesden Popper series of material, and I'm not going to introduce more complicated crystal structure in this set of lectures. And I would like to move now from crystal structure to not yet full electronic structure, but at least how the different electronic orbitals split due to the crystalline environment, especially in the neighboring oxygens. So this goes back a long way, like what, 90 years ago or so, and was pioneered by Hans Bethe and also Van Vleck in the 30s. I guess shortly after the completion of quantum mechanics. And it starts from the following observation that if you take an isolated atom with spherical symmetry, then you have, of course, 5 d orbitals, because d orbitals corresponds to L equal 2 and 2L plus 1 is 5. So we have 5 components of the d orbitals that we could simply label according to spherical harmonics. So YLM with L equal 2 and M ranging from -2 to 2, 5 values. And however, in the actual materials we are interested in, we don't have spherical symmetry. The atoms are, as I mentioned before, importantly encapsulated in this little cage of oxygens. The crystal structure breaks the spherical symmetry. And as a result, the degeneracy of these 5 components of the D shell, which result from spherical symmetry, will be lifted. When we break a symmetry, we lift degeneracies. This is a general principle of quantum mechanics. And one can classify, using group theory, how this lifting of degeneracy works. So if we have a cubic crystal structure, with octahedral environment of the metal, like in the cases I presented before, without distortions, just to start with, purely cubic, then it can be shown that the 5-fold degeneracy of the D shell is broken into a lowest lying triplet, which is called T2G. I think G means gerade in German, as far as I remember. And a higher lying doublet, which is called EG. So there is a simple physical reason for this, which is illustrated in the following slide. This can, of course, be shown by group theory and can also be documented by simple electrostatics, which will come in the next slide. But just with hand-waving argument, this can be understood fairly easily. If you think about the dxy. So now we need to use a basis of orbitals, which is no longer the spherical harmonic basis, but rather a basis which are linear combination of spherical orbitals, which are well adapted to the cubic crystal symmetry. In technical terms, linear combinations that transform as irreducible representation of the cubic symmetry group. And this leads to cubic harmonics, which are called xz, yz, and xz, and also x square minus y square and z square minus r square. There are specific combinations of these spherical harmonics, which are designed to form irreducible representation of the cubic group. And if you look at the members of the T2G representation, so x, y, xz, yz, you see that here on the bottom left, the orbitals of the metal are not directly pointing towards the oxygen. The oxygen is here, they are pointing 45 degrees away from the oxygen. So they will pi bond with the oxygen. While in contrast, the orbitals of the EG representation, and this is just 45-degree rotation of that, are pointing towards the oxygen. And so they were sigma bond. They are gonna sigma bond with the p orbital of the oxygens. And you can immediately understand that obviously there will be an electrostatic cost, which will be higher in this case than in this case. so that the T2G orbitals are favored as compared to the EG orbitals, because the T2G orbitals point away from the oxygens. Incidentally, this also means they tends to point toward the rare earth, and this is actually important to understand some of the aspects linked to distortions. So this can all be formalized by simple theory that will come later, but the same kind of group theory exercise that is done with the cubic group can be done by those who know group theory, at least, for lower symmetry structures. So if you start elongating the C-axis while keeping A equal B, which would lead to what's called a tetragonal symmetry group, then you can show that the T2G degenerate, threefold degenerate, manifold. Here, this 6 is because there is spin, okay, 2 times 3, is split between the lowest lying singlet and a higher lying doublet in tetragonal symmetry, and again, EG is also split. And then in the orthorombic symmetry group, this is completely split into 1, 1, 1, 1, 1. Of course, these splitting are typically smaller than the splitting here if the distortion is not too large. But they can be very large if the elongation is very large, like in cupretes, for example. So there is this lifting of degeneracy, which is very important. The basic one is this one here between T2G and EG. That's often called whatever, 6DQ or something like this in jargon. But this splitting is typically very large, several electron volts in oxides. And let's understand a little bit better how we can calculate this splitting just from perturbation theory considerations and electrostatics. Let me mention before I do that, the octahedral environment typical of perovskite is not the only one that is found in oxides. There are many other ones you can think of. There is notoriously the tetrahedral one, where the metal is surrounded by only 4 oxygens. But there are also many other ones that are listed here. And each one of those corresponds to a different pattern of crystal field splitting that I, of course, don't know by heart, but are listed here in textbooks. So how would you turn these qualitative considerations into more quantitative calculations? So as I mentioned, it all starts with writing the hydrogenated wave functions in the usual way. L is equal to 2 and M runs from -2 to 2. If you are in cubic symmetry, it's a good idea to make linear combination of these guys, which are written here, to work with cubic harmonics, which transform into this irreducible oppositations of a cubic group. And we have to understand how the metallic ion interacts electrostatically with the charges on the oxygen of the oxygen octahedral cage. And you can think of this as an electrostatic problem where each of the oxygen creates point charges and generates a potential, which has the cubic symmetry structure, which is written here, which is due to the 6 point-like oxygens acting on an electron at position R. So now it's a question of perturbation theory, and because the distance between the oxygen is relatively large, you can actually expand in R over D, where D is the lattice spacing. And it turns out that this is very convenient because the expansion of the Coulomb potential involves itself spherical harmonics. So there is a spherically symmetric part, and then there is a part which is which can be expressed, it turns out, into L equal 4 spherical harmonics. And then you will just treat these terms as a perturbation theory. So this is really first order perturbation theory. We take the wave functions carefully written in our cubic harmonics. And we take the potential elegantly expanded here in these spherical harmonics. And we can easily compute then these matrix elements. And we're going to find that indeed all the members of the triplets give a certain value, while all the members of the EG doublet give another value. And this difference, which is told 10dq, sorry, not 6dq, for whatever reasons I never understood, this splitting between the triplet and the doublet is given by this formula, which involves the charge of the nuclei, the charge of the electron, the distance between oxygen and metal, and some integral of the radial part of the wave function. So that's the basic theory that was introduced 70 years ago, no, 90 years ago, to understand the splitting between T2Gs and EGs and in oxides. But basically its physical content is what I was saying before, namely that oxygens, that the T2G points away from the oxygens while the EGs point to the oxygens. So you could say, why do we care about energies and crystal field levels? Well, we care a lot because the levels that are occupied by electrons are obviously given a certain number of electrons in the D shell, the lowest one in energy. And they are the crucial ones that determine the partially filled levels that are crucial for physics and chemistry. And typically there will be a competition between two energy scales. One is the crystal field splitting that we just introduced, but another one is a matrix element of the Coulomb interaction that I'll introduce later in the lecture, which is called the Houches coupling. And this coupling tends to favor equal occupancy of the different orbitals. So there is obviously a competition between the crystal field splitting, which favors occupancy of the lowest orbitals, and Houches coupling. And this leads to materials when the crystal field splitting wins, which are in the low spin configuration with a number of electrons in the lowest lying levels, versus materials where the Houches coupling wins, in which electrons are more distributed between the different orbitals, hence leading to more high spin configurations. So that's one of the reasons. This is really important. And as we will also see later in the lecture, the crystal field determines in a very important manner whether the system is a Mott-insulator or whether it's a metal, because the criterion for the Mott transition, or more specifically the ratio between interaction strength and bandwidth that is required to reach a Mott-insulator, depends crucially on the effective degeneracy of the shell. So whether you have electron in a T2G shell, which is threefold degenerate, or in an EG shell, or whether the T2G shell is completely split by additional distortions, changes these considerations and plays a very important role. And then, these considerations about crystal field are also important for your enjoyment of nature, because importantly, they also determine the color of minerals. And I couldn't resist putting this nice picture about why is ruby red. Once you know crystal field splitting and d orbitals, you already know why ruby is red. Ruby is a small amount of chromium 3 plus impurities, which is a 3 electron spin 3 half configuration, which is substituted into boring band insulator, aluminate, and which is a large gap transparent insulator. And the crystal field between the T2G and the EG shell turns out to be in this material 2.2 eV. So this value, or if you want in terms of wavelength, being about 560 nanometers, means that everything which is between 1.8 eV and 2.2 eV, which is basically red light, will pass through the crystal, but everything which is higher than that will be absorbed, and as a result, the material is red. So this is why ruby is red, and this is why crystal field is important. I also mentioned that crystal field is important, or the effective degeneracy of the shell, which is not 5, it can be 3 if T2G or 2 if EG, is also important to decide whether we have a metal or an insulator. And this is illustrated here. So this is perhaps the first simple theory plot that I show in these lectures. And this theory plot depicts the critical value of the on-site screen Coulomb interaction, the infamous Hubbard U, with respect to bandwidth. So this is the vertical axis versus the filling of the shell. So here 2n is like 6, let's say, if you have a T2G shell. So that would be half filling, 3, and so on, all the way to 6. And what you see here is depending on the degeneracy of the shell. So, you know, n could be 1 if you just have 1 level, 2 if you have 2 level, 3 if you have 3 level, and so on, 5 for a full D shell, degenerate D shell. And this is the plot of the critical U versus the filling of the shell and versus the degeneracy of the shell. And so what you see here is that, interestingly, the largest the degeneracy, the hardest it is to reach the Mott insulator. So the larger U you need to get to an insulator. And what you also see is that the half-filled shell, which is the middle of this plot, seems on this plot to be such that it's the most difficult to convert to an insulator. So this is actually completely wrong physically. We know that half-filled shells are easier to make insulating. They require much lower U. And the reason for this is because of the Hund's coupling. This calculation here, I quoted the reference, but this calculation ignores the Hund's coupling. And as you will see later in the lectures, if you include the Hund's coupling, these plots do not look like this, but they look exactly the opposite like that. And this is all due to the Hund's coupling. So because the Coulomb interaction is more complicated than just a Hubbard U, the actual tendency of a shell to become a Mott insulator is much stronger at half filling than away from half filling. So it would be much easier to convert a T2G material with D3 occupancy into an insulator than it is if the shell was D2 or D1. And it's important to take into account all the components of the Coulomb interaction or the screen Coulomb interaction to account for that. Okay, so now that I've told you about crystal structure of perovskites and also crystal field splitting, I would like to put this a little bit together and tell you how we can control or how these materials, how the crystal field is affected by the structure of the material. So putting these two structural and electronic aspects together. And this has to do with distortions that I mentioned before. So I already mentioned that there are different types of distortion. I mentioned two of them, tilts and rotations. So tilts are typically rotations around the A or B axis, and rotations around the C axis. That's more or less standard terminology, I think. But we can also think of other types of distortions, which would be more like intra-octahedral distortion, where we could take an octahedra and elongate it along the C-axis, for example. That's called a Yan-Taylor distortion. And that often appears when the electronic configuration is nominally degenerate, because that's a way for the system to lift the electronic degeneracy. There are other types of distortions. One often studied by our chairman is the off-centering of the B cation, which would lead to a ferroelectric distortion. And we can think of other distortions like in the nickelates, where there is a breathing mode structural distortion. So there are many, many distortions of this crystal structure, of the ideal crystal structure. But let me introduce a little bit of terminology related to tilts and rotations. And this comes with the infamous Glaser notations that some other speakers in these lectures may sometimes use. And it took me a long time to understand what they are. So I thought, why not put it in the lectures? So what are the Glaser notations? So as I mentioned, we can think of tilts and rotations. So we take the 1, 0, 0, 0, 1, 0, and 0, 0, 1 crystallographic axis, and this defines 3 rotation angles, alpha, beta, and gamma, with respect to this axis. So be aware of the fact that when we are talking about rotations, for example, along the C-axis, this means that we rotate the octahedra along the C-axis. So nothing happens along the C-axis. The rotations are taking place physically in plane, right? But we rotate along the C-axis. And the Glaser notations indicate the relative amplitude of these different alpha, beta, gamma by a letter. So if this letter is the same for all three components, that means alpha equal beta equal gamma. And then it also contains a superscript, which is either plus or minus, depending on whether when you look along the corresponding axis, the rotations are in phase or out of phase when you go from one layer of octahedra to the next. So this is an illustration of this Baroque notation here, where you look here from the z-axis. So you look, what you see is the AB plane if you want. You look along the z-axis. And what you see with your eyes, I guess, is that these octahedra are rotated. You can't see if they are buckled because we are not looking along the A or B axis, but that would be additional information you need. But you obviously see that they are rotated. So this is why here there is A0, A0. This means no alpha and beta are 0. But there is a rotation along C. And you also see that this rotation is out of phase when we move from one octahedra to the next. So this is why there is a minus. So this is the depiction of a crystal structure that has A0, A0, C minus Glaser rotation pattern when we look around the z-axis. Okay, so yeah, I'm just mentioning this because this is kind of useful, perhaps.
Antoine,
yes.
We're getting close to the end, so maybe
yes, I know.
Warning before the questions, something like that.
My watch is telling me that I've been speaking 1 hour and 23 minutes.
Excellent.
So, so give me just like 3-4 minutes to complete the infamous Glaser notations, and then I'll stop and we'll do electronic structure next tomorrow.
And we'll take questions. Perfect.
And we'll take questions. Yeah, and I can take many more minutes of questions, no problem. So tilts and rotations typically double the unit cell, as you see here. You know, this would be an ideal perovskite structure. This is the rotated guy, and obviously you need a bigger unit cell to describe this than that. And correspondingly, this also leads to new Bragg peaks, okay, in the X-ray diffraction spectrum. And obviously, as you tilt and rotate, you also lower symmetry. So if you start from the cubic, which would be a 0, 0, 0, and you start rotating, there is a correspondence between the Glaser pattern and the crystal symmetry that you are getting. And for example, if you are in the AAA configuration where alpha equal beta equal gamma, then you will get a rhombohedral symmetry group. If you are in the A00C minus configuration, then the symmetry group would be tetragonal because A equal B and so on. Okay, so I will spare you this sort of tables, but you should know that they exist. And the thing I would like to end the lectures on today is that when you elaborate your material, for example, by controlling strain through the substrate in thin film synthesis, this can influence the tilts and rotations. And often the question in the field is actually to understand how the known structure of the substrate propagates into the material that you've grown on it. And I want to emphasize that there's been beautiful recent progress in scanning tunneling electron microscopy, for example, to be able to say something about that with really beautiful images that are being produced in the past few years. Imagine also the oxygens, which is notoriously difficult. But often in our professional discussions on these materials, there are all sorts of discussions about what do we know about the rotation and tilt patterns of the material that has been grown on a given substrate. It all has to do how you accommodate strain when you grow a material on another one. And I just want to introduce one sort of general, almost generally valid concept, which is illustrated here, which is that when you grow a material, in a compressively strained way, namely such that the lattice spacing of the substrate is smaller than the natural lattice spacing of the material you're interested in, the bulk, then typically what you get is that you have rotation along the c-axis that develops. So the bonds along the c-axis are straight, but you can tune with compressive strain the in-plane metal-oxygen metal angles, which obviously, as we'll see tomorrow, will have direct influence on the bandwidth. When you grow the material under tensile strain, the opposite happens. You typically straighten up you typically undo the rotations, so you get more straight bond angles in plane. But then the system buckles and leads to alpha and beta rotations. So this is an example of density functional theory calculations coming to the rescue, where what you see here is a calculation in one of these nickelates, lanthanum nickel 03, under a given strain. So to the left is compressive strain, expressed in percentage with respect to equilibrium. So it's negative, it means compressive strain. And to the right is tensile strain. And what you see is that, and what you see is a calculation in red of the in-plane, well, in-plane, meaning rotations along c-axis, gamma angle. And here, the rotations along A and B axis, alpha and beta. And you see that when you are compressive, you have a non-zero gamma and alpha and beta very small, while it's exactly the opposite on the tensile side. So this is to illustrate the fact that strain is an important control parameter, not only to change the distance between atoms and hence the overlap of their wave functions and hence the bandwidth, but the story is actually more complicated because the angles change and you can make certain bonds more straight and certain other bonds less straight, depending on the sign of the strain that you apply. And all this has interesting consequences for the electronic properties of the material. And this is just a plot of some of the table of some of the commonly used substrates, and there are many others in Darrell's lab or in Jean-Marc Triscon's lab, and the corresponding tilt system in Glaser notation of these substrates in the bulk. Okay, so I'm going to stop there, as I mentioned, but I'm sure this will be covered in other lectures, and it's not for me to cover this, but there are some nice progress in scanning turning electron microscopy to actually monitor these distortions and whether or not they propagate more than a few atomic layers. And just to announce the menu of next session tomorrow, I now need to take you from structure, crystal structure and crystal field splitting to the full band structure of the material. So I'll do that, taking some concrete example. And then we need to continue onwards, including interactions more seriously than what band structure typically does, and understanding what interactions does in terms of physics. And I'll try to cover most of this in lecture 2. Thank you.
Thank you, Antoine. Now it's time for questions from the participants. In the chat, I've seen one question so far, but and I'll ask Professor Georges that question. But if others of you have questions, please raise your hand with that Zoom feature, and then I'll call on you.
So that's either because the lecture was so clear or because everybody's already sleeping.
Actually, I have 2 questions now, so I think it's warming up. Okay, so let me start. Let me start with the first question, Antoine. And this may be unfair, but the question is: does cerium nickel oxide exist? It's you showed all the rare earths and you didn't have cerium on that plot. And Yorick asks,
this is actually a very good question. And I'm not going to risk saying whether it exists or not. I'm just going to say that I've never seen it or heard of it.
I cheated, Antoine. I looked.
But I can also Google the same way that you are doing right now, Darren.
So
I was not sharing my screen.
I did find a publication actually from this year that reports it in nanocrystals in the perovskite form. So, but it wasn't really a fair question.
So I guess the fair answer is yes, it exists. Darrell just found it on the web. But to say the least, I think it hasn't been, it's fair to say it hasn't been thoroughly studied as far as I know.
Right. Okay, now there's a second question. This comes from Xijiao Huang, and it's about crystal field theory and ligand field theory, and asking if you could comment on how these two theories differ.
Well, I wish I knew. Yes, well, obviously, the crystal field theory involves ligands as well, right? Because I've just talked about oxygens and how they create an electrostatic potential. So that was a key element of understanding crystal field splitting. But admittedly, I just considered one octahedron, right? And one thing I totally ignored in this business is also the ligand-ligand interactions, which are presumably somewhat important. So, well, I mean, I'm not so familiar with these semantics, but I would imagine that ligand field theory is treating better the ligands beyond what I just presented. But I'm not an expert. But probably you know better than me the answer to this question, maybe, Dara.
Well, Andy Millis wants to.
Yeah. Okay. Wonderful. So Andy, I'm sure, has a better answer than me.
Go ahead, Andy.
All right. Can I say so? Can you hear me?
Yes.
Okay. In practical terms, there is no difference. Just don't worry.
That's what I would say.
That's the short answer. Okay. Now, the longer answer is that for basically uninteresting historical reasons, people use the term crystal field theory to refer to essentially electrostatic effects. If you have an ion which is surrounded by point charges, your transition metal surrounded by oxygens, which you view as point charges, then you have electrostatic field contributions which couple differently to different symmetry D levels.
Which I just described.
Yeah, which Antoine just described. So that's just the physical, Coulomb field from point charges distributed in some way. Ligand field really means the additional effects associated with hybridization and the related level repulsion.
And I actually also believe that ligand field theory is often used in the context of molecules, even more than actual crystals.
Yeah, but what it comes from is the hybridization contributions as opposed to the electrostatic contributions. And as Antoine said, really for our purposes, we don't care where it comes from, we just care how big it is and how it follows from, symmetry and structure and things like that. In practical terms, in almost all these solids, the actual electrostatic contribution is quite small, and the ligand, that is to say hybridization contribution, is in practice the dominant one. But anyway, that's
one thing I would like perhaps to answer also in broadening the question is that the simple-minded calculation that I presented should not be taken as yielding a quantitative answer for a given material. Of course, in a full crystal, we have bands, and what we are talking about is the typical energy separation between, say, the center of gravity of these different bands. And the simple-minded theory I presented is supposed to give you some ballpark order of magnitude of the splitting, but a more substantial calculation will require treating the whole periodic crystal, which I will get to to consider tomorrow.
But if I may add, I mean, it's, Antoine, you're selling your calculation a little bit short. What the thing you gave us also does completely correctly is, if it's carried out correctly, is give you the symmetry.
Oh yeah, absolutely.
So it tells you what kind of effects will happen, which levels are split.
Oh, sure.
Who goes up, who goes down. It gives you all that perfectly correctly. You just shouldn't rely on it for magnitudes.
Yeah, exactly. So this is the sort of table I showed, right? This sort of thing, which really is only symmetry consideration. More questions?
Yeah, there's the next is from Ruby Kim. Can you unmute yourself, Ruby?
Yes. Actually, thanks for a nice lecture. I understood lots of things today, and thanks for explaining that why Ruby is red today.
Ah,
I understood.
that's great. Yeah, that also resonates with your first name.
Yes, exactly. But my question is from the crystal field splitting of T bands, because I understood that when crystal there is the transition in a crystal structure, then the symmetry breaks. That is correct?
Okay. Can you repeat the question? Yes, the atom has spherical symmetry. When you start putting the atoms together in a crystal structure, obviously you break the spherical symmetry, and hence you lift the degeneracies of the D shell. Is that what you mean?
Yes, yeah,
yes,
right.
That's
like,
correct.
Yeah, actually, when like we have, if we have strontium titanate, and it goes from cubic to tetragonal transition around 105 Kelvin. So correct. I should think that this degeneracy is lifted below this temperature.
Well, so, okay, so what will happen, as you see, I think currently exactly on this slide here, in the cubic phase, you will have a fully degenerate T2G shell, right? Which will be separated by an EG from the EG doublet, higher in energy. And as you go into the tetragonal phase, because you elongate the C-axis, then this T2G will additionally break into a singlet, which will be lower in energy, and a doublet, which will be higher in energy, right? And again, this is easy to understand. Well, I mean, higher or lower in energy depends on whether the C-axis is compressed or elongated, actually. And it's easy to understand why. I mean, if you compress the C-axis, the XZ, YZ will be disfavored and then higher in energy. And if you compress the C-axis, if you elongate the C-axis, it will be opposite, right? So this sort of considerations, which are purely based on group theory and electrostatics, tell you how the pattern is changed.
Thank you.
Does anybody else have a question? If I don't see any more hands raised. Last chance for today. We tomorrow we'll have a longer question time.
Sure.
Anybody else with a question? Well, seeing no additional questions, Antoine, thank you very much for an excellent part one, and I'm looking forward to part two tomorrow.
Just should be one more, Daryl.
Oh, one more.
Yeah, there's one more, Ricardo.
Yeah. Hi, Antoine. I have seen crystal field splitting, in particular, for instance, in pnictides, where the orbitals are reversed sometimes.
Yes, sure.
So what defines the order which the orbitals?
Well, so again, I mean, there are two aspects to this. So there is pure crystal field effects, which have to do with the local environment. So I refer you to this thing, right? Where, I mean, the best example is comparing octahedral and tetrahedral, right? Where here in the octahedral, the EG doublet is higher, here it's lower. And you can understand that also from the way the orbitals point to the oxygens. Then in the case of the pnictides that you are mentioning, we are going to get into this ligand field versus crystal field that we were discussing a moment ago, because hybridization effects play a very important role in the pnictides. The pnictogen orbitals are extremely fat and large, right? And so they will hybridize strongly with the iron orbitals. So there is an interplay between pure electrostatics between the metal and these orbitals, and also hybridization.
Okay, thank you.
Are there any more questions?
Okay. So on the menu tomorrow, we'll be going into electronic structure of these oxides, and then, you know, strong correlations and how to describe them.
Great. Thank you, Antoine.
Okay.
See you tomorrow afternoon at 4:30.
Right. Same time, same place.
There is a morning session, guys. So so indeed, you will hear Antoine's second lecture tomorrow afternoon, but tomorrow morning there is Philippe Gauzès, and at 10 a.m. Paris time, and I hope that many of you will be there to listen to both.
Yeah, it's only 4 a.m. Cornell time.
Okay, so thank you all. Bye-bye now.